Hey everyone! Today we are going to explain something subtle but incredibly important in machine learning, statistics, and signal processing. Why is the maximum likelihood estimate of variance is biased? And more importantly, what this has to do with degrees of freedom, geometry, and the chi-square distribution. Let's start with a simple experiment. I simulate 100,000 sets of Gaussian samples. For each set, I compute the maximum likelihood variance estimate and the unbiased variance estimate. And here is what we see. The maximum likelihood estimate consistently underestimates the true variance. The orange histogram is centered exactly at the true variance, which is 1. The blue histogram, the maximum likelihood estimator, is shifted to the left. So why does this happen? Let's set up the problem cleanly. We observe independent Gaussian samples with mean mu and variance sigma square that equals to 1. And there are two cases. Case 1, the true mean mu is known. Case 2, the mean is unknown and must be estimated from the data. And as we will see, this tiny difference has a huge impact on the variance estimator. First, let's handle the easy case. The mean mu is known. The maximum likelihood estimator of variance is simply the average of square deviation from mu. And when the samples are Gaussian, this sum of squares follows a chi-square distribution with n degrees of freedom. The mean of the chi-square distribution with n degrees of freedom is n. So the mean of this part equals to n, and the mean of the maximum likelihood estimator in this case is n times sigma squared divided by n, which is sigma squared. So that means the maximum likelihood estimator is unbiased. Here is the simulation result. The scaled maximum likelihood estimate histogram can be perfectly fitted by the chi-square distribution. And in this case, there is no bias for the maximum likelihood estimate. The maximum likelihood estimate works pretty well. But this assumes we already know the true mean. In practice, we almost never do. Now let's look at the real world. The mean is unknown, so we estimate it using the sample mean. The maximum likelihood estimate looks almost identical, but the distribution completely changes. The sum of the squared residuals now follows the chi-square distribution with n-1 degrees of freedom. The mean of the chi-square distribution with n-1 degrees of freedom is n-1. So the mean of this part is n-1, which means the mean of the maximum likelihood estimator is n-1 times sigma squared divided by n. So this means the maximum likelihood estimator in this case is biased. Here is the simulation result. The histogram of the maximum likelihood estimator, the blue one, is cleanly shifted left. In this case, the mean of the maximum likelihood estimator when n equals to 5 is 4 divided by 5, which is 0.8. So the key question now becomes, why does estimating the mean reduces the degrees of freedom by exactly 1? Let's bring in the geometry. When the mean is known, the residuals are simply x, I minus mu. Each residual is a free Gaussian variable. There is no constraint linking them. And that means the residual vector lives in the full n-dimensional space. And visually, this is what happens. Let's consider n equals to 3. Each sample generates a residual vector in the 3D space. With the true mean known, these points fill in the space freely. This is what it means to have n degrees of freedom. Here, n equals to 3. But when the mean is estimated, something dramatic happens. The residual formula is xi minus the sample mean. And these residuals satisfy a strict constraint. The sum of the n residuals equals to 0. We can easily show that the sum of the n residuals equals to the sum of the n samples minus the sum of the n sample mean. So this part equals to n times sample mean, and this part equals to n times sample mean. So the final result is 0. This constraint forces the residual vector to a m-1 dimensional subspace. That's how the residual vector loses 1 degree of freedom. In 3D space, this subspace is a plane, the plane where the residual components sum to 0. In n dimensions, it's an n-1 dimensional hyperplane. And this geometry explains the change in the degrees of freedom. We lost exactly 1 dimension by estimating the mean. Now everything fits together. For ML estimator, when the mean is known, the residual lives in the n dimensions. The variance follows the scaled chi-square distribution with n degrees of freedom. The ML estimator in this case is unbiased. When the mean is unknown, the residuals live in the m-1 dimensions. The variance follows scaled chi-square distribution with n-1 degrees of freedom. the maximum likelihood estimator is biased low. For the unbiased estimator, it is defined as the sum of the square residual divided by m minus 1. So this division corrects the degrees of freedom loss. The unbiased estimator is unbiased. So here is the final takeaway. Estimating the mean forces the residual to satisfy one linear constraint. That removes 1 degree of freedom. The ML estimator does not correct for this, so it underestimates the variance. And that, in geometry, probability, and intuition, is exactly why the ML variance estimator is biased.